So essentially, the directory is the way that you access your file. So if you look at the cloud at the bottom, they're stored somewhere, right? We haven't talked about where they are yet, right? And the files may have different kind of permissions, different ways of accessing it, and so on and so forth. Directory is the way where we can access the files, right? And this is important because in the case of memory, you ask the kernel, and the kernel is there all the time. It knows all the structure. In the case of file systems, you may reboot the system, still has to keep track of all these data structures. It can't be kept in memory. It has to be kept in the storage itself, right? And one of the ways that you organize your file systems is you can access the whole disk as such or divide it into partitions. Essentially, you're splitting the big file into big disk into a couple of small disks. But within each disk, you have to store the directories, right? And you have to store the file contents. And this is what you'll do for your homework project too, right? You have to figure out some place where you have to keep the directory entries, right? And which tells you where the files are, right? And in the illustration, the directory entry is on the top. Is that significant? Yes. You're saying yes?
I would think so because then you always need to find out information about what files are in the directory.
Yeah. So the answer is, yeah, it doesn't have to be in the top, but it has to be someplace where you always know where to find, right? Remember, like this is for your homework project too. When you open your disk, right, you have to kind of bootstrap, right? You have to kind of know stuff about the disk. So usually you'll have a little bit header before that which says what kind of a file system these are and stuff like that. And then you have to know where the directory is, because directory is the one which tells you where the files are, right? So if you wipe out the directory, then I can't use the disk because I don't know what these are, because the rest of them just look like a bunch of blocks, right? Depending on how I organize those stuff, right? So directory entry, I have to know where to look for, right? It can't be something I search for. Once I know what the directory is, I can figure out where the files are, right? So you tend to keep it on the first, up in the front. Or for your project, it has to be someplace where it cannot be learned from the disk. It has to be known a priori, right? So within the disk, within the directory, yeah?
I was going to ask, when you store partitions on your disk, do they have to be stored contiguously, or can you store them in different places?
They can be stored in different places, but the same rules apply, right? Some of you may have partitioned your hard disk, right? You typically would want to partition it and say, this is something, right? And let's say this is / and this is /user and so on. You want to use it as something, right? So again, the disk comes to you as is, and you have to know how to do the stuff. And this is called the process of formatting, right? You format the hard disk, and then you set these stuff. And then you have to have a little partition table here, right? Or somewhere where I know where to look, which says that there are 3 partitions. One is here, one is here, one is here, right? And this has to be on the hard disk. So if any of you have looked, partition their own machine, right? If this partition table gets corrupted, you can't use the partitions. And then once you have the partition, you may have direct entries here. If this gets corrupted, you can't use the partition. Right? You can't use that particular partition, right? So yeah, so when you format the hard drive for a particular machine, somebody has to know how to read this partition table. If you can't read the partition table, then you don't know what these partitions are, and the whole thing fails. So who do you think should know how to read the partition table? Let's say for the operating system partition, right? Let's assume that Linux is here, right? And the Linux kernel is here. Who would need to know how to read the partition table? Is it the bootloader, right? Which is the one which, bootloader or the BIOS or the OS. Let's leave this now, right? Yeah.
Bootloader.
Yeah, it has to be the bootloader, right? Because bootloader comes before the OS is loaded, right? So all these things have to be known to the one prior to who's going to use it, right? So before the OS can be loaded, somebody has to open the disk, know where the partition table is, and interpret it to say this is where Linux is. And then the bootloader may have to know that the file that I'm looking for is this, which happens to be here, right? It has to know where to find the kernel, right? Where to find the operating system, so operating system can be made to run, right? So all this has to be done by the bootloader, and the bootloader has, so you are only allowed to partition the disk in a way that the bootloader can read, right? And the same thing, so once the operating system runs, it doesn't have to worry about the partition because it's already read by the bootloader. It has to know how to read the directories, right? So they all kind of cascade into each other. So all these are magic. All these are in some locations decided for whatever reason, but they cannot be read dynamically, right? The bootloader has to do it before, and so on and so forth. Then different bootloaders, and the different bootloaders expect certain things different way, right? And that's why you can't just take a disk which is partitioned for one kind of machine and put it in another machine and expect it to work, because it has to be reformatted, right? You might have seen it. You might have seen if you take in a CD which is burnt in a Mac as a Mac file, put it on Windows, he'll say, do you want to reformat it? Because he doesn't know how to deal with that, right? Right. So within the directory, right, the set of operations that you want to do is create new directories and delete directories, list the files in a directory, and so on and so forth. The typical operations you would expect to access the files. And the key stuff you want to look at here is the efficiency, right, in terms of, so every file that you access in the file system has to go to the directory. So if you expect to be accessing lots of files, you expect the directory structure to be efficient in telling you where the files are, right? On the other hand, if you don't expect to be opening a lot of files, you don't really care, right? You want the naming to be convenient to the user, right? There are certain things which are convenient to the system, but you want the naming to be convenient to the user, right? For example, a 64-bit number would be very convenient to the system, but not necessarily for human beings. And you want to be able to group them, right? And this is a concept that we have all used to, because you have directories and subdirectories. So you have subdirectories for your course project, and so on and so forth. You don't like to put them all into one big soup and then try to figure out what files belong to what, right? So over the years, there are a number of different ways of organizing the directories. The most simplest one is have a single level directory, right, where all the files hang off this one structure, right? And it's simple, right? It's simple because when you try to implement this, you have to have one directory and all the files hang off there. Searching could be a problem because now you have to search through the whole list to find what you're looking for, right? And there's no notion of a grouping or anything. All the files are here. So this works on cases where the system is very simple, doesn't have too many files, and you know precisely where the files are. It doesn't work for multi-user kind of system, right? So if AFS were to do that, that means everybody in Notre Dame will have one directory. Everybody can see everybody else's file, right? And you have to choose one unique name that is unique across the whole campus, right? And that's not going to work. But if this is a computer which is run or car, is trying to manage your transmission or something, right? It doesn't really look, it's not doing a whole bunch of stuff, so it can work with this stuff, right? For your project, this is fine, right? You don't have to do anything more complicated. You're free to do it and get extra credit, but you don't have to do it, right? So more complicated mechanism was two-level directory. VAX VMS used to use this model, where you have, for different user, you have single level tree, right? And so within the user, you have the same issues that we looked at before. Essentially, you have one directory, you put all your files there. It's up to you to figure out what files belong to what. But different users can have the same name, right? All the users can have a directory called A, right? But within a single user, there's no structure, right? And these systems also make sharing harder because now I can't just say I want to access the other A. I have to say this A belonging to user 3 and so on. So I need to encode all that into my system. So naming may not be as efficient as you would expect, you would like it to be. Right? A more general case, this is what we tend to use these days, is a directory, a tree, right, where you have a hierarchical name structure, right? And there are no restrictions on how many levels you can go for the most part, and there are no restrictions on how many files you can have in each directory for the most part, right? Obviously there are limits, but the limits are fairly big. So essentially, this is simple. It lets you create large directories. It lets you manage them according to projects, and this is what we are used to for most of the modern operating systems, right? And Windows and Mac and Linux and all support this kind of model, right? So the searching is efficient because now you don't have to search the whole system. Now you can say, search in my projects directory what the file I'm looking for, right? And it has a grouping capability because you're supposed to put the related files into the same directory, and now you can have a notion of current working directory, right, which restricts the search, right? So if you do something like cd to a certain directory, and then you say access a file, you access the file in the current working directory, right, rather than giving the exact name all the time. And that makes the stuff a lot more easier to deal with. Otherwise, you have to say the exact full path name to open a file. You don't have to do this within these systems. So that's the notion of the absolute or relative path name. So essentially, you can say, this is the absolute way of saying stuff, right? Or I could do cd right? So if I were in the directory /user/lib, I can do a ... which goes back up the tree and then bin ls. So this is relative to where I am currently. This is absolute, right? I can use this wherever I am. This is relative to where I am, and so that's that, right? So one of the things that some of you may have, I think it tripped up some of you when you first came to the Linux machines, where the Linux machines have a notion of a path, which is similar to what your Windows machine has to, where you give a list of directories where you want to search for your program, right, and run the program. So you run ls, you don't actually run /bin ls or something, because it figures out what the program is, right? So many of you compiled your program, and it created a program on a current working directory, and when you tried to run it, it did not work, right? So you had to do /prog, right? Remember the first time you had to do that, right? So one of the things I said was this is usually done because it's considered a security violation to put dot in your path, right? The reason is if you forget where you are, if you did a cd to my directory, right? And this is usually the tilde is a little way to say go to my directory, right? If you went to my directory, and then if you did prog, right, by mistake, if you had dot in your path, then you'd be running my program, right? And you don't want to do that because my program could essentially delete all your files or what have you, right? So you don't want to do that, and that's why typically you don't put the dot in your path, and that's why your programs fail. But we're so used to relative path names, we don't even think about it. We just go to any directory, go to cd ... or whatever, and access the files, right? And this is the model that we use for the most part. And when you do a make dir, which is creating a new directory, it creates in the current directory. So you can either use relative or absolute, right? So you can say make dir /temp /some file, or you can say make dir dot or or what have you. And you can do the remove dir and all those things. So the problem happens when you would want to share these files across different users, right? So there's no reason which prevents you from naming a same file in two different directories, right? And doing so may be convenient because, for example, a particular file called count may be the same for both of us, right? So, for example, for the project too, the traces, I can put them all into your directories by making them point to a single thing, right? So these pointers, we don't define what they are yet, right? They could be soft pointers, which mean that every time I come to one of these count, then resolve what these values should be, right? That's a soft link. Or it can be a hard link which says that always point to this particular file, right? The problem with you having something like this is if you delete the file for count, right, from one side. So if you're coming from the spell side and I delete spell/count, right? Now that means if you come to the dict side, that won't have anything pointing to it. So that it may have a dangling pointer, right? So to avoid dangling pointer, you may have to have double pointers so you could go back and trace back and fix those. Otherwise, you'll have a dangling pointer, right? So you have a file which is pointing at nothing, right? So somebody on this side never deleted the file, but somebody on this side deleted the file, so you can't access the file anymore, right? And that's even more of a problem if you have directories, right? If you have directories from where you're looking. So suppose the directory words was linked here, and if you delete the directory, then a whole bunch of files would go away, right? So a whole bunch of files would be hanging orphaned, right? So that's a problem, and that's why typically you're not allowed to link directories, right? If you link directories, then a lot of bad things happen. Yeah.
I was going to say, with this model, would it be possible to actually create a cycle if you had maybe the child of W7 be one of those higher directories?
Mm-hmm. Yeah. So you can create cycles, right? And some cycles are okay. Some cycles have to be fixed, right? For the most part, file systems don't really care if you have cycles. If you have a cycle, if you keep going through a cycle, that's fine, right? You might have seen that happening in AFS most of the time, right? How many of you seen creating cycles, right? So so again, this goes to another philosophy of operating system, which is if you want to shoot your own foot, go ahead, right? I mean, as long as you don't destroy the system, it's fine. So if you want to create a loop and you keep going, that's fine. The OS only cares if what you're doing affects how things should perform, right? So in the case of the directory, if I have a hard link and I delete the directory, then the others may be left dangling for no reason of theirs. But you're free to have cycles the directory tree. Yeah, so if you have two different names pointing to the same directory, if one of them deletes it, if one of the set deletes it, then you have to define what happens to the other side, right? Either the other side should also be deleted, right? Or you have to keep a notion of a count, right? You have to keep a notion of count to say this particular file is being accessed by two different people. So when you delete it, you only release one count, right? So you don't see it from one side, but the file still lives on and then will be deleted when the count goes to 0, right? And so the arrows that I mentioned could either be, it's a link. It could be done when you're accessing the file, or it could be done statically. Statically is a hard link. At the time when you want it, is a soft link, right? Many of the things that I say sounds Unix-y, but it's mostly true for Windows too, because all these were rolled into the POSIX standards, which Windows is part of it too. So Windows supports many of these operations, even though you may or may not be aware of it, right? And I'll show you one mount operation which is not typically used in Windows, but Windows supports that too, right? Yeah, so in the case general directory, you can have all the stuff. You can have loops, and you can have directories pointing to by different paths, and those are okay. And most systems support that, right? So you could guarantee no cycles by running some algorithm to make sure that there's no loops in your directory. But most file systems let you have loops, because loops only causes you to get lost, right? So if you create a loop in a directory, and if you keep going into the directory, you keep coming back into the directory, right? But it doesn't do anything bad to the system, so that's okay. So the next notion is once you have the next notion is the notion of namespace, right? So let's stay with the hierarchical namespace because that's the most interesting stuff, which means that there is a root, right? And then you have a bunch of directories hanging around here. So this is a typical file, the view that you see when you log into a machine, right? So the question is, what happens if you have a new disk, right? If you have a new disk, and let's assume that this disk has like files like so, how do you graph this onto here, right? So if you have a single namespace structure, then you want to somehow take this part and graft it somewhere here, let's say here, right? And that operation is called mounting. So essentially you say, from this point, once I do this mounting operation, right, I can access / I can go, let's say this is user, and let's say this happens to be. So I can say /users /Surendar would get me to this particular disk, right? So this particular file system or this particular stuff gets grafted into this namespace, and that's how you build a larger namespace by essentially operation called mount, right? In fact, that's what you do for your homework project. The homework project, your fuse file system, you would mount it into the file system. So whenever you access something here, it goes into this file system here, or in your case, it'll go into your file system, right? And you could do this in Windows too. So Windows typically, when you add a new disk, it creates it into the, the old way is to use the A:, B:, C:, whatever, right? So each disk, so essentially you used to have right. The traditional Windows notion or traditional DOS notion is every new partition you have will show up with a different letter, right? So you have A:, B:, they are like hanging around like a forest, right? There's no unifying stuff, right? So if I want to access so I'm allowed to have user, a directory called user in all the different partitions. So I need to access it as A:, /user, whatever, and give this thing, right? But you don't have to do that. You can do the same mount operations in Windows. So you can make it A and B are traditionally used for floppy disk or whatever. So you can say, let's say if you have a D, you can mount this here and not show this at all, right? People rarely do it because the system tends to prefer the CD kind of thing to be compatible with the DOS ones, right? So I'm guessing most of you are Windows users, right? How many of you have used something like a mount to keep them all organized? So that's a good thing you can try today, right? Like the mount operation, you should be able to do mount help to tell you how the stuff is, and essentially, make it look like the Unix kind of thing. You can have multiple disks put into one namespace, right? By default, you have this ugly. I call it ugly because you have to. I call it ugly because one of the ways is when you do the relative directory, like relative path names, you have this notion of you can say A:, which changes the relative root from something to A, and then you can do this, right? You can do A:, CD user, right? These two together define where I am, right? If you're using Windows, you would know that I have to specify these two, right? If I change this and I say CD user, I'll be in a different. Actually, let's say this is like this, right? Right. The example I gave was you can use this to set your relative directory, but you also have to specify which disk you are part of, right? Whereas in the model that you want, you just want one relative path, not two of those, right? You may not have realized all this stuff if you're using the GUI file thing, even though it actually shows what directory you are, right? So that's the notion here. So if you have something like some directory structure inside your file system, right? The B file system has its own directory structure and everything, but it's kind of hanging off without a root. So you have to glue it into the root file system. So within the root, now if you mount it at a certain point, everything becomes relative to that particular root. And you can unmount it, put it in another location, then everything becomes part of that, right? So if you change the Jane part and mount it under Sue, then it'll become /user/Sue/Jane, what have you, right? So you can mount it any which way you want, right? And from the OS perspective, it does not care how you do it. If you keep moving it like that, then it becomes confusing, but that's not operating system concern. Right. So the next aspect is so at this point we have figured out how to have this notion of names. We introduced the notion of namespaces and how you can glue a bunch of file systems to create this sort of global namespace as a hierarchical namespace, right? What you really want to do is share files, right? So it's possible that I can have a root, and this is user 1, and this is user 2. And this user and this user never interact with each other. They live separately and all those things, which is one model. You can use that. What would be interesting is if these two can share a file, right? So they have a file here, right? And they can share a file, right? They can either share the file by just accessing it together into one path, or you can leave it belonging to here and access it as a absolute path to the other user, right? But the key here, what you want to do is you have two programs. They want to be able to open file, right? And they want to be able to open file and operate on them, right? And this is the notion of sharing. And this is very similar to your notion of sharing from memory pages, right? You want both these things to be sharing them such that if this one writes something, you have to be able to read them, right? And that's the notion of a sharing, right? So if you open the same file for sharing, if one of them modifies it, the other should be able to read it, right? Which is what you do with the shared memory, because when you do a shared memory, when one modifies it, one can read that, right? So of course, you have to make sure that the protections are fine. People can be sharing those. But once you do that, this is what you want to do. But the problem, again, is file systems don't have to be within the same machine. They can be across the planet. So even though this is what you would like, even though this is what the semantics you would like, you can't support that for anything but the local machine. If you're using a distributed file system, you cannot make sure that this write will be shown on the other side, right? So the actual sharing model is a lot more complex, which you have to understand. And that depends on the particular operating system that you're using, right? And this will be something that you'll go through in a distributed storage or distributed systems class, right? How many of you shared a file read-write between two people, two processes? Did you say yes?
I don't actually know.
Okay.
I changed my mind.
Okay. That's not surprising, because one of the things that some of the studies have found that people rarely share files amongst different users, right? Because they may share libraries and stuff read-only, which doesn't really matter, because if it's read-only, there's no concern, right? Read-write sharing is very rare, right? If you do have to share within AFS, the semantics are pretty complex, right? So unless you know what the semantics are, you can't do it, right? The AFS semantics for write sharing is last writer wins, right? Right? How many of you heard the term? There's one who says, heard of the term, right? So I'll try to say it because it's important, because we use the system here, right? And if it's not clear, I mean, there's the classes for that, right? So essentially the idea is if you have two processes which are trying to open a file, right? they could be different machines, right? So when you open a file for write, you get, let's say, a token, right? And when you open a file for write, you get a token, right? The specific ordering of who gets a token first does not, this is a distributed system, so you can't really say this goes first, this goes next, but somebody got it. Like let's just say this got it first, this got it second, right? So within AFS, there's also a notion of callback, which means that file system can tell you the token is no longer valid, right? As long as the token is valid, you're allowed to modify. So you're allowed to modify, you're allowed to modify, right? And if somebody else comes here and they want to read, right, they'll be able to read the prior copy or whatever copy that is in their cache. When somebody writes it, right, let's say this one does a close, right? Then you will send a message to all the other clients to say, whatever you are reading is invalid, your cache is invalid, you have to restart again, right? So every future person who comes in will get this copy. Who gets to read will get this copy. Even though this is allowed to write it, because it continued to write it, right? So if it continues at this point and if it closes this file, right, the future reads will have to go from here. Whatever write was written here would be last. Right? So it's the last writer wins because the last writer is the one which gets to hold. Whatever you did before would be used by people who come before this happened. So between this time and this time, all the reads would be reading this file. And this time, from this time on, whatever written here is completely lost, right? But if you don't understand that, AFS would be very confusing because you opened a file, you modified it, you wrote it, you closed it, and bang, second later, it's all gone, right? It's completely gone because this won, right? That's about the end of time, but more details are, you should take the distribution class and you can have the Wednesday.